Alright, we finished last time in our discussion of the respiratory system talking about the different forces acting on the lungs, forces that help the lungs to expand and forces that contribute to the lungs collapsing. And we need both of those forces acting correctly at the right time to allow us to inhale and exhale. So be sure that maybe even just draw a simple diagram of the lung using arrows to demonstrate what direction the different forces are on the lung. And for example, compliance is the ability of the lungs to expand. So that would be an arrow acting away from the lung toward the thorax. And another one we said was surfactant. Surfactant allows the lungs to expand because it breaks up that water surface tension. So that is something that allows the lungs to go outward. We also said the elastic recoil of the lungs promotes the lungs to contract or to, with exhalation to get smaller. And then we also said surface tension acts inward to deflate the lungs after inspiration. So compliance and surfactant act outward on the lung, pulling it outward. And the elastic recoil and surface tension act inward on the lung, pulling it inward and promoting collapse. Again, we don't want it to collapse, but we do need it to recoil inward during exhalation and get smaller to allow that air to leave the body with that CO2. So today we're going to talk about the pulmonary volumes and how we measure the capacity of the lungs to participate in gas exchange. So there's a couple of terms we need to know. This tidal volume is the volume of air that is inhaled and exhaled during quiet breathing. And if we look at the graph here on the next slide, if my thing will cooperate, we can see tidal volume here is this, the volumes are shown in this bar. So this movement of air in and out, this would be inhalation, exhalation. So we see about 500 milliliters of air. If we compare this to a healthy adult male, about 500 mils of air comes in and 500 mils of air is exhaled out. So that's in a healthy functioning lung, 500 in, 500 out. We call that volume tidal volume. Inspiratory reserve volume is after we do a normal inhale, how much more can we inhale beyond that if we needed to. For example, if you inhale to yawn, for example, that's usually a much larger inhale than a normal quiet inhale. So how much more room is there in the lungs for extra air to be inhaled? And if we measure that, we start at the top here where we have just a normal quiet inhale of 500 mils, and we measure that all the way until the lungs can no longer expand, and that would end right about here. So that value is about 3,100, or this particular diagram it says 3,000 milliliters of extra air that can be inhaled after a quiet inhale. So we call that the reserve, inspiratory reserve. And then if we look at the exhalation, after a normal exhale of 500 mils, how much more can be exhaled? For example, if you were suddenly laughing hysterically, or if you were coughing, those would be examples of maximum expirations. And if we look at that volume, that's a lot smaller. That's only about 1,200, or in this case 1,100 mils. So we can inhale a lot more than we can exhale. And if you think about why that would be important, is if we exhaled all the air in our lungs, our lungs would collapse, and that would be very bad for gas exchange, because gas exchange is occurring even between breaths because we have air from the previous breath that is still in those alveoli to keep them expanded. So that's what we call the residual volume. That's the amount of air left in the lungs that is undergoing gas exchange. So it's important to understand that we don't want to exhale all the air in our lungs because our lungs would collapse if that happened. So this residual volume, which is about 1,200 mils, is what's available for gas exchange. And I shouldn't say all gas exchange, because some of it can be in the airways, in the lower airways, not in the alveoli. So that is the expiratory reserve volume and the residual volume. So if we look at a graph like this, this might happen when we're looking at somebody's lung function, say a person with asthma or emphysema. We want to see where they're at when they first come into treatment, and then we're going to see if there's any improvement after we give them, suggestions on how to improve their lung function and prescribe medications to help with that process. So this is what a spirometer spirometry graph would look like. And you'll actually see one of these and use spirometry in advanced A&P if you have to take that class. So if we combine these volumes, we get what we call pulmonary capacities. So if I look at inspiratory capacity, and we're looking at this slide here, looking at the different capacities, it's just a combination of different volumes. So if we look at inspiratory capacity, that just means how much air can be inhaled into the lungs. So we look at the tidal volume, the 500 that's inhaled during quiet breathing, and then we add that to the maximum inspiratory volume, and that's where we get our capacity, our inspiratory capacity, this number. So it's just these two numbers added together. Vital capacity means what is the total amount of air that's being exchanged across the lungs. So for that we would combine what is inhaled with what is exhaled. And that number is 4,600. And then total lung capacity is how much total air fills these lungs. Then we have to bring in the residual volume, the volume that is not considered into the inhale and exhale per minute or per breath, but it still represents the amount of air in the lungs. So we just add all these different volumes together to get the total lung capacity. So I'm not going to ask you to memorize these numbers, and you'll probably be asked to make a calculation based on the numbers and looking at the graph for the test, but I won't ask you to memorize these values because that's not critical information. You can always look that up. So looking at gas exchange across the respiratory membrane, we talked about that, and across the tissues, there's a couple of different factors that determines how well a gas can diffuse. So first of all, how thick that membrane is one factor that determines how well a gas diffuses, and also the diffusion coefficient of that gas, for example, how that particular gas can dissolve in the membrane, and that's just a standard value that we see for some gases, and we find that carbon dioxide can diffuse, has a higher diffusion coefficient compared to oxygen, so it diffuses much more readily across the membrane. And then looking at the surface area, if there's a large surface area for diffusion, that is going to increase diffusion. And the higher the partial pressure difference on one side of the membrane to another, that will also increase diffusion. So we're going to look at those factors now as we investigate how these gases move from the lungs to the blood or from the tissue to the blood or vice versa.